Thank you so much for being here. I'm Masruk, as Pastor was saying. So today I'm going to present the current work that I'm doing right now in my master's, and it's called Revisiting the Age Scale of Galactic Globular Cluster. First of all, this is not going to be a talk on astrophysics, and certainly not going to be a talk on physics. Okay, so I'm going to talk more about data analysis. Okay, and how are we using data analysis to explain stuff. Okay, so okay, all right, okay, bye. Okay, yeah, it works. All right, so okay, one request: if you have any question, feel free to interrupt and ask me. I will. There will be some jargons that will be. I don't know. I don't think it will be familiar for you. So feel free to ask me the question like right at the moment. It will be easier for me to explain. Okay. Okay, cool. So why are we interested in globular cluster? That's the first question. Okay. So you can see that there is an image of galaxy formation, and if you look here, it looks like a cloud of gas, and they collapse and they start forming like galaxy, forming stars like this, and after like few giga years they start to form a disk, and after so many years it becomes like galaxy that we observe today. But if you look at the second image, you can see that there are already some star clusters. So to clarify, you can observe two kind of star clusters in a galaxy. One is called open cluster and one is globular cluster. The fact about globular cluster is they are formed in like first few giga years of the galaxy formation. So you can say that they are formed pretty early during the galaxy formation. Okay. Now, why is this important? And you will find most of the galaxy clusters in galactic halo, and the open clusters you will find it in the disk. Okay, so it's more or less scattered in all over this spherical shape. Okay. Okay. No. All right. So as I said, this globular cluster they act like a time capsule. Okay, if you can determine the age of a globular cluster, you can certainly set a limit on the, at least a cutoff age limit on the age, right? If you find a star that was born in first few giga years, and you can say that okay, this is the age of the of that star, you can certainly say for sure that this galaxy was formed this certain age like years ago. Okay, so that's why they are pretty crucial to study. And also in most of the galaxies, not in most of the galaxies, in Milky Way, we can see that there are a few clusters whose properties are like a little bit different than the most of the clusters. So you can always also think about, you can also have information about the mergers, because like people assume that those clusters were accreted, they were result of the merger, like there was a galaxy before and there was Milky Way and they merged together and the clusters were accreted. So studying globular cluster is very important to determine age, also to understand galactic dynamics, how our galaxy evolved. Okay, now in this project I'm going to use I am using these three data sets. One is from APOGEE. As I go along, I will discuss, or I will try to explain what it is, and then photometric data and astrometric Gaia data. Now, well, let's see. Okay, Now we need to know first of all, like how do we determine age of a cluster? So, yeah. Oh, okay. A cluster of star is a like a bunch of star. Like this is a set of star which is like formed in a like closed. How do I say? They are bound by gravitational force. That's it. But there are a group of clusters. They are like all together. Well, you have like thousands of clusters that forms a galaxy.
They do have gravitationally bound planets and so on.
Yeah, they have their own dynamics. Right? Yeah, there's just a bunch of stars. If it's like a spherical shape, we call it globular cluster. If it's in a random shape, we call it open cluster. Okay. So I'm more like interested in globular clusters. So if you find a globular cluster in a galaxy, these are like pretty old stars. So they were formed in first few gigayears of galaxy formation. No, not really. If I go back, if you can see here, like it's all over the galactic halo, like in the. So they were formed in first few gigayears. But as you can see that the newer stars, they are formed in this disk. So they are more massive and like more bluish. Okay. Yeah, like they emit. Okay. Now I will ask a few questions just to know if we are on the same page, that you understand what I'm talking about. How many of you know about HR diagram or color magnitude diagram? Okay, so I have to explain what is an HR diagram. So first of all, this is an example of an HR diagram. So as I go along, I will explain what is magnitude, what is color index, and everything. But as you can see here, on the x-axis, there is a difference between two magnitude. Once again, I will tell you what is a magnitude. So apparently the magnitude is, so you have a star over here and you have your telescope here, and you just measure how much the flux is on your telescope. Okay. And on the y-axis, you also have another magnitude. So if you plot all the stars in this plot, you will find a shape which is like this. Okay. Initially, all the stars, they form this line which is called a main sequence, this straight line. And as the stars they grow old, they start shifting from here to the right. And you can ask like, why is this? As I told you that the thing that we are plotting are the magnitudes. Practically they are flux. So as they grow old, the flux changes, right? And you start like seeing pattern on them, and they start shifting towards right. In layman term, that's what happens in all the clusters, and you find a shape like this. Now when you have a galaxy cluster and you have a HR diagram like this, now what people do is people have like prepared model that are known as isochrones. Okay, and you can twist and tweak the parameters. You can find them online. Okay, and you try to fit those isochrones with your HR diagram. Now this point over here is called main sequence turn off, like where it starts to turning the other way. Okay.
What are we talking
the magnitudes. I will go as I go along. I will explain what a magnitude. You can plot absolute magnitude. You can plot apparent magnitude. It's. Yeah, they do evolve. No, like let's say that the galaxy the star cluster is formed today. So all your stars are going to be in the main sequence, right? So so as you go higher on the main sequence, you go the mass increases. So the star over here has the lowest mass, and the star over here has the like bigger mass. So the star which is massive, they tend to like burn the hydrogen faster, right? Right? So and then when they finishes burning hydrogen, it starts to like burning helium, and then suddenly you see a change in the magnitude, like the flux. Of course, it changes its color and temperature and everything. So you will see a difference in the flux. So it starts moving towards right. In the y-axis, we are plotting magnitude. In the x-axis, we are plotting difference between two magnitudes. I will discuss what is the difference between, like, you can also see there is a thing called b minus v. I will discuss what it is. So this is called color index. These are just jargon. You don't need to know about this, but I will try to explain what it is as I go along. But the important thing is you have your theoretical isochrones like that you can download from anywhere. You have a bunch of websites, and like if different universities, they develop their own isochrones based on their own stellar evolutionary model, and you try to fit this main sequence turnoff and also the what we call is the subgiant branch, and these isochrones were based on a few parameters known as metallicity, alpha abundance, and age. So you can get the age from that isochron which has fitted the best with your HR diagram. Okay. Now, what is the metallicity and what is alpha abundance? Once again, I'm going to explain as I go along. Okay. So this is the thing that you need to know, that we have a HR diagram and we are going to fit it with some isochron. Okay. Okay. All right. So metallicity. Now, in like we can say that metallicity just measures that how much of metal you have in your star apart from hydrogen. So for astrophysicists, once again, not me, that you know what is a metal for them, or for us, I guess. Anything higher than helium is a metal. Okay. So what you do here, the term metallicity, it takes the ratio between number of iron and number of hydrogen, and it normalized by the metallicity of the sun. Okay, and we call this term metallicity. And if you have a metallicity higher than 0, then you call it metal rich, that is higher than sun. And if you have it less than 0, we call it metal poor. Now, why do we need this? We will see. And okay, this is a logarithmic expression that essentially tells you like how much iron you have inside your star. Let's see. And the next thing we need to know is alpha abundance. So these are the higher like heavy elements other than iron. It can be magnesium, titanium, whatnot. But the number of alpha elements divided by number of iron, and you take the logarithm and you get the alpha abundance. That's it. So why do we need alpha abundance? So you see the most of the globular clusters, they are old stars. So they are metal rich. So you have heavy elements there. So once you are discussing about the stellar evolutionary models, you need to discuss those models which is alpha enriched. Right? We cannot say that this is a new star and they don't have heavy elements, and we cannot discuss our things using the metal poor or like less alpha abundance or solar like, we cannot treat them like solar like stars. That's the gist of it. But yeah, any questions? Of this thing? Okay. All right. So once you have alpha abundance that is greater than 0, we say that these stars are pretty old. Okay.
Why?
So old stars tends to, they burn, they start at the end of burning the hydrogen, they start burning helium, and after burning helium they start to burn, build all, make all these heavy elements, right? So the presence of elements, heavy elements, is in the old stars, and if it's equal to 0 or less than 0, you say that okay, they are not that metal rich, or they are like newer stars. Okay. All right. Now, the metallicity. Now, you don't have to know all these things by heart. I also don't know. That's why I have those slides. Okay, so I am using like APOGEE data, and that's where I'm getting this data from. So what I'm doing mostly right now is reading the data and plotting some data and everything. Like I will show you what I'm doing, but the gist is I'm using APOGEE data from data release 17, and I have selected 33 globular clusters in Milky Way. Okay. And this APOGEE data is for my metallicity and alpha abundance. What I do is there is a thing called membership probability. So once again, this is data analysis. So the data file tells you if you have a star, what is the probability that this star belongs to that cluster. Okay. So it can be a star that, you see, you cannot say for sure that this one particular star, it belongs to that that cluster for sure. Like you have some probabilistic assumption, or what do you want to call it? But you have to filter. Okay, what did I do? Oops. Okay, so you have to filter out some stars which is like less probable to be the member of that cluster. Okay, so I'm taking the probability which is higher than 90%. Okay, so from the APOGEE data, and you can say that, well, why are you using 33 clusters? So APOGEE apparently observed around 72 globular clusters, and I took 33 because I have Hubble Space Telescope's photometric data from Hubble Space Telescope, and I just took the intersection between those two data sets. Okay. All right. So APOGEE is a spectroscopic survey, and it gives you the information about metallicity and alpha abundance. That's what I'm going to use. All right. So.
Why is there a probabilistic issue here? Because if I look out at a certain direction in the sky, I can see the star and how they are. I mean, I don't see how there would be a confusion regarding which globular cluster a star belongs to, right? Maybe I'm missing something. What am I missing?
No. There is a good chance that a star was accreted from another cluster, right? Yeah. Let's say you have one cluster in another cluster, and then both of them collided. Now you have like two systems going all together, or like. Oh, then there are other issues. I'm not entirely sure, but most of the time you cannot. Your resolution is too low to sometimes like distinguish two stars. Like you have a binary system, or you have a star that is far away, but you are just taking it to be a member of that star cluster just because it's too bright. Those cases can be like possible. Okay, now, so I am assuming all of you know about flux, right? Once again, you have a star, you have your telescope, the light is coming, right? And then what you capture in your telescope is the flux, right? So what is a magnitude is apparently the ratio between the flux that you measured and some reference star or flux of some star that you know for sure that, well, this is the magnitude of that star, and then you took a logarithm, and then this empirical formula gives you the magnitude of that star. Okay. All right. So there are like various types of magnitude. You can have apparent magnitude and you can have absolute magnitude, and I am not going into the technical details of these things, but absolute magnitude is, once again, you have a star, you have your telescope, you can have like number of things in between your telescope and between your stars, right? So you have to correct your magnitude for all these things there in between. Also, let's say that you have a star here and you have a star far away, but the star that is far away is much brighter than the star which is like closer to you. So they both can appear in the magnitude scale as same. So you have to take the distance for account, okay, to calculate the absolute magnitude, like how bright they are, just to make sure that you are not missing anything for the distance. So you can use this formula to calculate absolute magnitude from the apparent magnitude. But end of the day, we need this absolute magnitude to do what I'm going to do next. Okay. Now, in my APOGEE data set, I have color, that is difference between two photometric band. Okay. Once again, astrophysics 101. You have your star, you have your telescope. So the light is coming and you can put filters in front of your telescope. That is, you are just allowing light with one wavelength to enter inside your telescope, okay? And these are called filtering. And you can put like red filter and blue filters and whatnot. And there are many photometric bands that you put filter and you measure magnitudes. So this is a Gaia magnitude. You can see from here that this is G magnitude, and I have calculated I have plotted the HR diagram over here. And now you can ask, well, the HR diagram that we saw before was like something like a shape of, I don't know, inverse S. Now why is this like this? Because I'm just taking like a subset of that HR diagram, and this is called red giant branch. And you can see that on the color bar, this is the magnitude, and this thing over here is called horizontal branch. Not important, but you can see that the metallicity over here is not as, like, there is a little bit of discrepancy on both sides.
Colors to understand
you mean in the HR diagram? No, I wanted to see if all the stars that you have, if they have the same metallicity or not, if the metallicity is uniform or not. Yes, this is a later time, and for the simplicity, we are going to assume that the cluster itself has the same magnitude, same metallicity for all the stars. So that's what I'm doing. You put a histogram and you take the median, okay, and that's what you are going to use. So this is what a data analysis is. If you have a problem, make it simple, okay. Now that's it. So you can see that this histogram is a little bit skewed, and you know that these stars over here in horizontal branch, they are creating problem, and you can trust the horizontal branch more for the metallicity parameter, because they are the not the horizontal branch, the red giant branch, because they are old, they are red giant, they have like more metal rich things. So what I did, I got rid of that horizontal branch. Now all you have right now is the red giant branch, okay. Now you can see that, well, this is a very good looking bell-shaped Gaussian distribution, right? Now we can take the median and the standard deviation for the error bar, which is pretty important, by the way. So yeah, this is how I calculated the metallicity that I'm going to use for all the clusters. So this is one example. I did 33 of them, and you have to do like what is necessary for whichever cluster it is. Sometimes you have to clip something, sometimes you have to select them by hand and whatnot. Okay.
How do you start your measurements?
What do you mean?
Certain branch of thought. How do you trust the measurement?
Oh, no. For instance, when you fit these isochrones, like the theoretical models, you assume that your star, the cluster has the metallicity, the same metallicity for all the stars. So that's one parameter. Like for each metallicity, you have one isochrone. Like there is a set of isochrones. So each isochrone represents one age, one metallicity, one alpha abundance. And you pick one and you see if it is fitting with your data or not. So I'm taking one metallicity for all the stars. That is the median in the clusters. And I can trust the red giant branch the most with the metallicity.
Why is that?
Because they are the heavy star with all the like metal rich elements stars. Okay. Now, if we are done with this spectroscopic data, we start with HST photometric data. And you know what is the photometry is essentially like fancy photography. Okay. Once again, you try to take pictures with fancy cameras. And then you are also calculating the absolute magnitude here. You are taking two photometric band, that is two different wavelength, and you are taking the difference and you are plotting the magnitude. That's it. The same game that we are doing. And just to be sure that we are taking the correct magnitude, absolute magnitude, we are fitting with a theoretical isochrone just to see if it is fitting with the data or not, just to check. But yeah, here it's also the same, but we have to do another thing. This is called interstellar extinction. What is it? Is since you are taking pictures, you have to be sure that you are taking into account all the things that is in between your object and your telescope. It can be gas, it can be cloud, I don't know, so many things. But what you have to do, there is this, there is an effect called reddening and extinction. You can get it inside the data set, this interstellar extinction, and this is called reddening parameter. And you take those into accounts. You have standard formulas, and you can see there is a difference between. Huh? So your stars, because of absorption or like the light is coming through a dense medium, so it can absorb, it can scatter. So it can appear to be with lower, like less hot than the star, like how do I explain? So it can appear like reddish instead of like what its original color is. So that's called the reddening effect. No, blue minus visible. I am working on very local things, like inside the Milky Way. The Doppler shift doesn't vary. I mean, it does, but for my work, it's not that important. Yeah. That's a technical glitch. Okay. Now, this is another thing that you will find you will find you will find a lot of tools available to do data analysis or what you want to do, and I'm going to use a framework called spins. I will, but the spins it uses. Okay, I am assuming that all of you had done a course in statistics and probability and statistics. So, and how many of you heard about Markov Chain Monte Carlo, MCMC? How many of you heard about just Monte Carlo simulations? Okay. All right. So what do you do essentially is you generate random numbers with your computer and you try to compute something. And this Markov Chain Monte Carlo thing is based on Bayes theorem that you study in probability and statistics. So as apparently you have a model like a stellar evolutionary model in my case, and you have some data and you have some parameters. What you are trying to do is you are trying to find this probability of these things, which is called posterior distribution. So it's just how probable a parameter is based on your data and your model. Okay, and the formula goes like this. So this term over here, this is called likelihood. So you give your computer not a computer, you give your I don't know, system that okay, this is how likely this, so this parameter can be within this range, this certain range, and this is over here is called priors. So you give some initial values and your computer generates random number and it tries to get you the best model you can have with random number generation. Okay, but you don't really need to know what is going on inside because you have this framework inbuilt. So the spins, it works. This is a Python based tool. It was developed by these two people, Leberton and Rees. That Rees is Daniel Rees. He is one of my supervisor. And you can see here that it uses Markov Chain Monte Carlo and linear interpolation. Okay, but it is like a black box. Okay, what you have to do is you have to give your grid of models, that is your stellar evolutionary model. You can download it from anywhere in like from the internet, and you have to make it as like spins compatible, and you have to put it inside, and then you give your magnitude that we calculated from our data, right? The metallicity and the magnitude that we got from our photometric and spectroscopic data. Now what it does is it takes all these things and it runs Markov Chain Monte Carlo at that MCMC, and you can get output like age, metallicity, mass, whatever you want to get, like the whatever the stellar parameter you want, you can get output from that. Okay.
What is systematic?
Oh no, that's just this is the name of the software. Like,
how do you? What is the output that you get?
You get output your age, metallicity, and mass.
So it lists according. It lists the clusters according to the age, metallicity.
No. Can I use the board? I think I. I think it's. Awesome. So what I'm telling here, grid is like it's like a 2D grid, like it's a matrix. So you have your grid like this. Now what are we taking is I'm giving this magnitude and the metallicity as my input, that is okay, that is this thing over here, the prior, right? So in the model it can fall like, do I have any different color? No. So it can fall anywhere here, right, for one star. Now what it does is it tries to use this interpolation, and then it runs the MCMC. So this model here, grid of models, it contains the like the theoretical isochrones and everything inside it. So after you like infer your MCMC with spins, it tries to find the best model that fits with this data that you gave, and it gives you like the parameter like age, metallicity and mass. So you can twist and tweak the code to find other parameters as well, because the grid contains everything, right? In my case, I'm just getting age, metallicity and mass. And the question that you asked, like how sure are you that you are getting the right results like metallicity? You can see that I'm giving a metallicity as my prior. That's my best guess that I'm taking the median, but I'm getting a metallicity out of a statistical analysis, right? So that's how I'm just using this data to just telling the computer that, well, you have to start finding from this point, but the best model is going to be found from the MCMC by itself. Okay, have I made myself clear? Okay, any more questions? No? Oh, I haven't gone there yet. Well, now this is a very good thing. You just input all these things and you have the age as your output. But there is a problem, right? The problem is this is extremely time consuming. Okay, so I am using a cluster computer that is called Tycho. PSL has a, like, we have a few supercomputers, but once again with 4 core and with 111 stars, it takes around 36 hours. So this is extremely time consuming. Okay, and one of my friend who was working with Daniel Rees, and he was trying to like address these issues. He was trying to optimize this software like spins, but after like 4 months of work, he like made it, I don't know, 1% efficient, like the previous one. Actually, he got rid of this interpolation thing and he introduced some machine learning stuff. So with large data set now, we don't have the convergence issues. Like with MCMC, you encounter some convergence issues. So I'm not going into all these technical details. I'm just talking about the outliers, that what the results are and everything. But okay. Whoa. Okay, I think it's fine. Okay, now, so what I told you all along is the methodology. I have to check whether my this methodology that we have developed is correct or not. So for that, I have taken this particular globular cluster 5053. And that was not completely random, and with the photometric data we can see the HR diagram over here, and the sequence is pretty thin, and thin sequence means less number of stars, right? And what we are trying, we are just like inside the spins, we are putting this main sequence turn off as like if I can date all these stars in main sequence turn off, I will essentially get the age of my globular clusters. Okay. Now, in this particular, you can see in this, I don't know, bluish color, we have around 700 stars, which is like extremely time consuming to compute. But the good thing about spins is you can analyze one star or you can analyze multiple stars. So I have chosen these 11 stars over here randomly, and I can present the results of those. So if you have one globular one star from main sequence turn off, the H turns out to be 12 gigayear with this error limit. Okay, and well, there is a package called EMCC, I guess, in Python that you use for running MCMC and gives you this particular very good looking plots which are known as corner plots. Yes. Oops. No, this is the age of one star in that cluster. And you also have this, well, this is very important, but at the end, you have all this 1 sigma, 2 sigma deviation, like with your median. So you can essentially have this posterior distribution, like a normal distribution, and your age, you can see that it peaks around 12 gigayears. Okay. And you can see that the initial mass and the age, they are correlated with one another. But you can see the metallicity and the the age, they are not correlated to each other. So metallicity essentially like has no correlation with age, but the mass, yes, it has.
Correlation, as far as I understood from your last comment, right? At the end of the lifetime of the stars, the metallicity, I think, increases. That's what I understand.
Yeah, but well, you have to see, like I am taking. Okay, if I go. Oops. Now, as you remember, like I have taken the metallicity to be like it's constant for all the stars. You remember, like I took the median and I treated it to be the same. So the metallicity of a star over here in the main sequence and in the red giant to be the same. So when you run your code, you see the effect of that thing, that they are not related to each other. Okay. Now, also, you can have you can run multiple stars, and you can see like I have taken 11 stars, and the age of this 11 stars all together is given to be like 11.6 gigayears with this limit. So you can, if I can run all the stars in the main sequence turn off, I can get an age for the whole cluster, like how old the cluster is, right? So that's the end goal. That I want to determine the age, a common age for all the stars over here that will tell me that how old my cluster is. Have I made myself clear? Okay. All right. So now you can see like I have like we have mass and we have age and the metallicity. So, and you have the posterior distribution. Once again, you can see that on the third column, I guess, yes, it peaks around, well, you cannot see it, but trust me, it peaks around 1200. Okay. It's not my fault. It's this. Okay. All right. So Now you can see that the result that we got is around this 12.25. That is pretty standard in the literature. So we can say that for sure that our method is producing like reliable results. Okay, but what we have right now is a computational challenge, right? It's extremely, so you have, this is the thinnest sequence that, oops, nope. I am not used to this. So this is the thinnest sequence. Okay, what am I doing? Yeah, okay. And if I go a bit up, and you can see this is NGC 104, and this main sequence turnoff is like pretty dense. And I calculated that in this particular region you have around 10,000 stars, which is practically like very like impossible, and I have 33 of them. Okay, now what I am going to do for next 6 months is I will try to come up with some, I don't know, some way to do these things for, and I have actually did something within last I don't know few weeks, and I'm going to tell you what did I do. But what you need to know is, yes, we have something that is pretty reliable in terms of the age. Now what it will help is if we have improved age on globular clusters of Milky Way, we can set a limit on the age of Milky Way, and I can send you some literature that discusses what is the significance of this thing. So there is a new growing field known as galactic archaeology. So what they are trying to do is they are trying to know the history of Milky Way, like how the galaxy was formed and how did it evolve. So knowing the age is the first step for that. Okay, and also there was a paper written by Lawrence Krauss in 2003 where he discusses about the determining the age of globular cluster is going to help what? Okay, it's going to help you with understanding like what would be the age of the universe itself. Because you can know that this is the oldest objects. So if you can just find the oldest globular clusters in all the, like in the universe, then you can certainly set a cutoff limit there. And there is also it's going to help us understand more about the cosmological constant, that is the dark energy part of the whatever you want to say it, but yeah. Now the thing that I'm doing right now is I have tried, so it's not here, but I can just tell you that it comes from the training of physics Olympiad. If you have a problem, you just solve it like a problem, that's it. So I cannot like run it on the run the spins on the like actual stars. What I can do is I can slice this HR diagram into multiple bins, like hundreds or 200 bins, and then I can just put one fake stars in each bin with the median and the proper error propagation, like the systematic error, also the like what is the thickness of this sequence, right, with the standard deviation. So instead of, I don't know, 1000 stars, you have only one. So in this main sequence turnoff, you can have like at best, depending on your bins, 5, 10, at best like 20 stars, and running 20 stars in spins is pretty like feasible. It's not that hard. Okay, so that's what I'm doing right now. I'm just developing the codes right now to do this fake star thing, and it is also producing some good results that I don't have right now to show you, but hopefully within next 6 months I will have something. Okay, so yeah, the goal is to analyze all these 33 globular clusters, and after that we will have a precise determination of Milky Way's age. And yeah, that's what I'm doing since last September. Thank you.